lossy case, what it says is that if you were to excite this system, the resonant mode of the system is actually complex, and it cannot have a sinusoidal steady state value. It cannot have a sinusoidal steady state value, and that's actually very troublesome. It means that if you look at something, it will decay. Okay, if there's a loss, loss can come from two manners. One is the fact that loss can come from the medium. Medium here, because K naught is actually omega mu naught epsilon naught. So if there's a medium loss, this could make this pole not on the y-axis. Another one is one that is forced by the radiation condition. In order to evaluate this integral correctly, as you've seen in your homework, you have to pick a path that satisfies radiation condition. You either have to choose to detour the path above or below the pole, depending on whether you want the kind of radiation condition satisfied. So oftentimes this summation is indeterminate. And in order to make it determinate, you impose the radiation condition. And when you impose the radiation condition, the Green's function becomes something like this. This is a Green's function in the scalar case that satisfies the radiation condition. But what is special about it? The special thing about this Green's function is that it's non-Hermitian. If you think of this as a matrix operator, you may use this to calculate the interaction between any 2 points. Its conjugate transpose is not itself. Why? Because it belongs to a lossy system. And in quantum mechanics, or you can learn from your matrix algebra, if a system is non-Hermitian, the eigenvalues are complex. If the eigenvalues are complex, it corresponds to time decay. Okay. So once we impose the radiation condition, we give rise to a kind of Green's function called a retarded Green's function. Retarded Green's functions don't have Hermitian properties, and they correspond to complex eigenvalues. And those complex eigenvalues correspond to time decay. Okay? So this is not a good system for physicists. At least it gets them very, very upset that things are not time harmonic. Because in physics, you study something called the time harmonic oscillator. And then you study something called a quantum time harmonic oscillator. Those assume that those harmonic oscillators are always in time harmonic motion and they don't decay with time. So this is a big trouble for them. Okay, this is a big trouble for them. So how can we define or think of a system where things don't decay? Where things don't decay with time? Yeah, well, there's something called the spectral Green's function. Which is the Green's function minus this Hermitian conjugate. Okay. If you think of this Green's function is not physical. It has a part that satisfies radiation condition. But if you take the complex conjugate and Hermitian transpose it, this part corresponds to one that does not satisfy radiation condition. Okay? It actually has the property that the wave grows in space, and this is usually called the advanced Green's function. This is called the retarded Green's function. This is retarded because it satisfies causality, and if you look at this way, if you take it to the time domain, everything is causal and nice. But this Hermitian conjugated Green's function does not have this property. Hence it's called the advanced Green's function. But if you look at this spectral function A is a very nice function because A is Hermitian. A is Hermitian, right? A is Hermitian. A is Hermitian, that means that you can have real eigenvalues. You can have real eigenvalues. So instead of having to deal with complex eigenvalues, like in this kind of system over here, in the case of loss, if we define that to be my Green's function, I come up with a Green's function where I can have eigenvalues being real. That's one good thing, okay? And second thing is that if I look at this system, if something is in time harmonic oscillation, it will always be in time harmonic oscillation, right? Because if something is losing energy to infinity, it's always augmented by another term that brings energy from infinity. This happens in the case of thermal equilibrium. If a system is in thermal equilibrium with infinity or with its environment, okay? I can have loss in the first system if I bring in the second system that way. In the equilibrium state, everything is oscillating in a time harmonic fashion. Okay, and that allows us to connect to quantum mechanics. All the oscillators that we have in the system can be connected to the quantum time harmonic oscillator because they are not decaying with time anymore. Okay, if you think of it, they're not decaying with time anymore. Okay, so let's look at this spectral Green's function more carefully and see what we get. We actually get something very interesting. Okay, I think it's very interesting at least. So you can prove that the complex conjugation of the dyadic Green's function is equal to, maybe it's like this. I think we learned this in our course, right? This is equal to that. Didn't we learn that? We learned this, right? We learned this. This follows from reciprocity. So if you were to do the emission conjugate of this, you would get this. Okay? You will get this. And then I think this should be this way around. If I put this R prime over there, then it works. Okay. So this then is equal to I G Green's function itself minus this complex conjugate. Okay. That if I make use of this property, then that becomes that. Then this becomes the imaginary part of the Green's function. So if you have the Green's function, if you just take its imaginary part, and you get this spectral Green's function, they actually correspond to a non-lossy system. And it can be time harmonic motion all the time. So let's see how we can take the imaginary part of this Green's function. So let's look at first this property that if I were to take the conjugation of the dyadic Green's function, I should take the conjugation of this. Okay, I should take the conjugation of this, and it will look something like this. And then let's assume that I have a lossy system to begin with, so K0 square will be conjugated. K0 square will be conjugated, okay? But then I can show very easily that Fn of minus K R is Fn conjugate of Kr. I can very easily show that. Go back to the 4 definitions or 3 definitions I have for my Fn. Most of the thing comes from the fact that all the Fn are proportional to this. So if I change my K vector, I just conjugate the vector wave functions. Okay, I erase them from blackboard. There are some other details that you might feel that might affect this property, but it turns out that this property is true for all the 3 vector wave functions that we have defined. So if that is the case, then this should be the prime here. I can change this K to minus K. Instead of sum over all K, I sum over all minus K. It's the same thing. Then I will reverse the transpose of that. So then this becomes just sum over k or sum over or minus k doesn't matter, right? And the only complication that remains in my equation then is this k0 star squared. Okay? So I can take the imaginary part of this by subtracting this 2. Subtracting this 2. But then everything else is the same. Everything else is the same. This is the same. The only difference comes from here. So my spectral Green's function, sometimes in books that just called a spectral function, will be just I, the subtraction of 2, okay, and then I will have k n fn k of r, fn star k of r prime, and then if I subtract the 2, the corresponding to this subtracting with that, which is the same as taking 2 times the imaginary part of 1 over kn squared minus k naught squared, where I can take out. So that is the spectral Green's function. I just take this one and subtract it by this one. There's a conjugation there. If I take this conjugation into account, it's just like taking the 2 times the imaginary part of that. That is my spectral Green's function. This corresponds to a system that can always be in time harmonic motion. And I can relate this system to quantum mechanics quite readily. Okay, any questions so far? I guess we'll come back after the coffee break and show that how this function is related to the local density of states. Show how this function is related to the local density of states. So oftentimes you'll find in textbooks that if you take the dielectric Green's function, take this imaginary part, make r n equal to r prime, you get the local density of states. Okay? We'll come back from the coffee break. Any questions so far?
Is there somewhere we can read about a 1D case, or there's not a vector case for this? Maybe does this work for the scalar?
I don't know. I don't know. I just figured this out myself. Okay, and then with an email from Shao Wei. Okay, he was trying to connect this to quantum transport in electronic transport. And a lot of these things are not in the literature, I believe. But they might be in the quantum transport literature. Okay. Okay. But I don't think there's a 1D equivalence of this. But any doubts on the mathematics so far, you can ask me. I can maybe help clarify those.
One thing weird was why is k, we're taking the sum of k, but before we had an integral with k.
Oh, we sum over k. You could convert this sum over k into an integral if you want to. But I think this is more elegant, right?
Right.
Instead of putting an integral.
But k is not this, or k can be.
K is discrete at this point because I use periodic boundary conditions. You can let a, b, and d become infinitely large. This will become an integral. But I think at this point it's a lot easier to think of it as a summation. You don't have to think about Jacobians and that kind of thing. When you do integrals, then you have to think about what the Jacobian is and so on. But right now we don't have to. Everything is discrete times. Okay? I'll come back.